Hello. Today, our lecture will be devoted to a reminder of how we should handle mechanical elements. To a large extent, this lecture will be a reminder of material available in any dynamics course. However, we will take deliberately a view that is systems oriented, that is, a view that will allow us to analyze these mechanical elements using the systems methodology that we will see later in this course on dynamical systems. So, our first task is to create a workspace within which we are going to discuss mechanical elements. Mechanical systems are among those that we will encounter most often, especially in the aerospace world, and they consist of many different things: airplanes, wings, ailerons, all that are part of an airplane. We will be talking about certain mechanical elements like springs, dashpots, and elements like that. We'll be talking about rods, elements that can rotate, and the like. The main exercise they will be facing is deriving the equations of motions for these devices. These equations of motion are differential equations. Not all of them will satisfy the framework that we are interested in following. That is, not all of them are linear. But we'll discuss the process of linearization at length in such a way that by the end of this part of the course devoted to mechanical systems, you should be able to bring a broad range of mechanical systems under the purview of this systems course. So let's talk a little bit about mechanical elements. From the dynamics course that you have taken in the past, mechanical elements are driven by a single equation named F equal ma, which is Newton's law. Now, sometimes you have seen variations on that theme. One of them is h dot is equal to the sum of the moments which also happen to be vectors. Now h is the angular momentum, and h dot plays the same role as ma, whereas the sum of the moments plays the same role as f, and to be more precise, the sum of the forces. With these two equations, we have been used in the past to capturing a variety of mechanical systems. In the context of this systems-oriented course, we will be first talking about core dynamical elements that we tend to encounter in real life. Among them, we encounter springs. Springs are drawn as follows. And they are characterized by a number of important variables. There is x1, the location of one tip of the spring, x2, the location of the second tip of the spring, assuming that the spring is horizontal. And we also have the force F1, which is the force exerted by the spring at the location x1, and F2, which is the force exerted by the tip of the spring, the right tip of the spring, at the location x2. In general, F2 is equal to minus F1. Also, there is a residual length that we call x0, and the residual length of the spring is the length of the spring when it is at rest. Often we will see that we assume x0 to be equal to 0, which is a simplifying assumption allowing us not to carry residual lengths throughout the calculations. The relationship between the force and the displacement or elongation of the spring goes as follows. F, which is also equal to F1, which is also equal to F2, with a minus sign in front of it, is equal to some k, which is a constant, times delta x, which is the elongation of the spring. Now, given that delta x is equal to x2 minus x1 minus x0, we finally get that f is equal to k times x2 minus x1 minus x0. Now, this is a reversible operation. We can also say that x2 minus x1 minus x0 is equal to f over k, which simply means that for a given force applied to the spring, it is going to elongate by this much. Other elements that we will encounter are variations on the spring, which are, for example, torsional springs. A torsional spring is usually represented as a spiral and satisfies the following characteristics. We assume that the inner tip of the spring is connected to an inner box which are represented like this. And the outer end of the spring is connected to an outer box now. The inner box and the outer box rotate let me show that. I show certain axes, okay, such that they both make an angle alpha and beta with the vertical. Now, the spring force restoring moment is equal to the force, is equal to a coefficient k times beta minus alpha 0. Beta minus alpha is the difference of angular locations for both supporting solids. Alpha 0 is the residual angle of the spring. And as I said, this is equal to the moment generated by the spring. We now can talk about masses and inertias. A mass M, which will often be represented as a rectangular item, is characterized by its position, its velocity, x dot, its acceleration x double dot, subject to forces, and the mass has m as its main characteristic. We know that Newton's equation that drives this mass, assuming of course the mass is moving along a horizontal location, is m x double dot is equal to F. Therefore, making and creating instantaneously the differential equation that defines the motion of the mass. Now, if the mass is in several dimensions, for example in 2 dimensions, then, and if the force is in 2 dimensions, if we call x the x-axis and the y-axis, we get that mx double dot is equal to fx, the component on the x-axis of the force, and my double dot is equal to fy. This is not necessarily the best way to represent things, but it sure does the work. Let's go now to inertias. By inertias, I mean objects that rotate. They could be like this, circular. They can also be like rods that rotate, etc., etc. The general equation that drives this system goes as follows. I times omega double dot or theta double dot must be equal to the moment applied to this device. Let me say a few words. The moments are those applied to the mass. Theta is the displacement, the angular displacement of the mass around a given axis. And this is, of course, not far away at all from the corresponding equation talking about masses instead, in such a way that masses and inertias pretty much behave the same way. Now, I must point that this equation is true if this is a fixed point or if this is the center of gravity. If it is none of the above, then it gets complicated. I invite you to look up your course on dynamics in order to have the proper expression when the rotation point is neither fixed nor the center of gravity. The inertia here is a function of the rotating object. It varies, for example, as follows. For a bicycle wheel whose spokes we neglect and whose rim we assume to be a circle, the inertia taken at the center of the wheel will simply be mr squared, where r is the radius of the wheel. For a disk, that inertia goes down. And if memory is correct, it becomes mr squared over 2. And so it is important that you memorize the inertias of a couple of important items. If you don't know how to compute the inertia of any item, you must be able to recompute it quickly. For that purpose, all that you need to do is remember that inertia for a planar object is equal to the integral of the square of a certain position plus the square of a certain other position times dx dy over the entire body. What do I mean by that? Let me erase dx dy for now. We will make it reappear later. And let's replace it with dm. For a body of interest, given a rotation point, we pick dm as a small element of mass here. We compute in a given coordinate system x, y, its coordinates x and y. This is the x and the y that appear in this expression. Now, let's, for example, compute this for a circle. Or to be more precise, a disk. The inertia will be the integral of the whole disk of x squared plus y squared times dm, which is the small element of mass here. Now, if we assume this is uniform density, then we have that dm is equal to rho dx dy in such a way that I becomes the integral over the disk of x squared plus y squared times dx dy times rho. Rho is the density. And this is where dx and dy appear. Now, this kind of integral is not easy to compute using such a coordinate system. Instead, we use a polar coordinate system. And all this is background material in such a way that the integral and polar coordinates, are called r and theta. Probably remember that. This integral is simply I is equal to, well, x squared plus y squared following Pythagoras theorem is r squared. Dx dy becomes r dr d theta. And then we have the rho that comes in front of it. Now, the boundaries of the integral are from 0 to the final radius of the disk. And the range of theta is, so that's for r, the range of theta is from 0 to 2 pi. Bearing that in mind and erasing what we don't need, we can say that that integral is the integral from 0 to 2 pi times, I'm going to put the rho in front of it since it's constant, times the integral from 0 to r of r cubed dr d theta, which is rho times 2 pi, the theta component goes right away, times the integral of 0 from r cubed dr d theta, which is r fourth over 4. Now, are we there yet? The answer is no. What we need to do is to simplify this expression to make the mass of the disk reappear. Now, the radius of a disk is r. The circumference of a disk is 2 pi r. The surface of a disk is m r squared. The surface of the disk times rho is m r squared times rho. That's the, my mistake. The surface of the disk is pi r squared. My mistake. The mass of the disk is rho times pi r squared. So you fill that into this equation and you get that the inertia of a disk would be m times r squared divided by 4. Well, this expression is not quite correct. If we look at this expression and we plug this into there, we do not obtain mr squared over 4, but mr squared over 2, which, by the way, is the expression that we have called back a few minutes earlier, straight out of memory. As you see, modulo computing errors and sign errors, it is always safer to have a way to recompute the quantities so as to be sure that the ones we have in memory are correct, or vice versa. Let me introduce another kind of element that we will be very interested in, which are dampers or dashpots. Or shock absorbers. Now, those dashpots or the dampers or shock absorbers are there to damp out the motion. For linear dampers, they are often represented as this. There is an initial position at one tip, an initial final position at the other tip, and then there is an initial velocity, there is velocity at the other tip. The dashpot is assumed to be massless, just like the springs that we have discussed earlier. This is not a perfect assumption, but it does a pretty good job. Then we will talk about the equations that drive the dashpot. If this is a force F1, if that is a force F2, then we have that F1 is equal to F2, and that is equal to a coefficient mu times x2 minus x1 dot dot. And so what this says is that the force generated by the dashpot is proportional to a coefficient mu times the difference of speeds between x1 and x2. A typical example where you're going to see that kind of a dashpot is in a car. You're going to have a wheel. The wheel is connected via a spring to the frame, but also via a dashpot. The spring is there to provide suspension. The dashpot is there to damp out the motion and therefore, as a matter of fact, prevent the car from oscillating forever. Let me draw this bigger. Here's your wheel. Here is the axis. Here's a platform going through the axis. We have the spring on the one hand. We have the dashpot on the other hand. And that is it. If you open the internet and we go over Google, okay, and we type car suspension, we probably see more of these. Let's go to images and let's zoom on the best possible picture we can find. I think that we can okay, let's pick this one. Okay, the spring is here. The dashpot or strut, that's another name for it, is hidden inside the spring in such a way that the combination of the two provides appropriate motion for a car as it goes through hoops. So that is the last element that I want to talk to you about. Now we need to interconnect those elements. And for that, I open a new file and I talk to you about, let me reappear here. I talk to you about interconnection. So the typical interconnection that we're going to see over and over and over again is the mass spring system. There will be plenty of variation in there. You take a spring, you attach a mass, the spring has stiffness K, we assume there is a force applied to the mass, F. We call the location of the mass X, X dot, and then X double dot. And we write the equations of motion. d dt of mx dot is equal to F minus K times X minus X0. That is the elongation of the spring times K. And when it's elongated to the right, it pushes, or it pulls rather, to the left. The good thing about this thing, I can also rewrite it as mx double dot is equal to F minus K times X minus X0, is that this is a standard linear differential equation. And therefore, if you want to make it fit inside our framework, it's very easy to do. Of course, we need to add the initial condition x0 and x dot 0, which are the initial location of the mass. But if this is the differential equation that we need to deal with, then its solution is trivial. What you do is you apply blindly the formulas that we have applied, or developed rather, during our lectures on the Laplace transform. So we know that x double dot, or to be more precise, the Laplace transform of x double dot is equal to minus x dot of 0 plus the Laplace transform of x dot and times s. Now this is minus x dot of 0 minus s times the initial condition x0 plus s squared times x. That's all we need in order to solve this equation, since we can now write the differential equation as m times minus x dot of 0, which is x dot 0, minus s x0 plus s squared x is equal to, well, the Laplace transform of f, which I can just write f of s, or f hat of s, minus k times x in the Laplace transform domain plus k times x0. Or in other terms, and let's again erase a few things here. With the given equations of motion, we obtain in Laplace domain that the solution reads as x times ms squared minus plus k, okay, for this guy, must be equal to mx dot 0 minus msx0 plus k x0 plus f hat, or x is equal to mx dot 0 minus msx0 plus kx0 plus f hat divided by ms squared plus k. Now, of course, the final solution to this equation depends on x0, x dot 0, and f. However, you can recognize that there is a denominator here which looks like s squared plus 1. That is the sure sign that you're going to have sines and cosines in the time representation of this solution. But I'll skip that, we'll talk about it later. One of the issues that we will often face when dealing with dynamical systems is the presence of nonlinearities. In fact, it can be easily argued that nonlinearities are everywhere. Therefore, our attempt at providing linear representations of the various elements that we are discussing is only a partial but very convenient representation of the systems we are interested in. It is very hard to analyze nonlinear systems from the viewpoint of an undergraduate class. Those of you who are interested in attending graduate school will see a lot more material devoted to nonlinearities and synthetic methods to not only analyze them, but deal with them. So, nonlinearities arise when the response of some elements is not linear. Here is a linear response, though not perfect. Here is the example of a nonlinear response. Such nonlinear responses are very frequent. They can be like this, they can be like that. Okay, they can have all sorts of shapes, including sometimes a broad shape. Each time, they may be either a result of nature, or they may have, in fact, been engineered. Some nonlinearities are good. For example, rate limiters for aircraft actuators. The way it works is that if the commanded rate of, say, an aileron is too high, then the system will not respond that fast, because too fast a response may mean burning the corresponding electrical motor, for example, or the corresponding hydraulics. For that, the rate actuator, the rate limiter, works as follows. If this is the input rate, that is the rate that's desired, and this is the output rate, then the response is as follows. For a good chunk of the range, the rate that is commanded, and then once we pass a certain threshold, then the response saturates. And you find that on virtually any aircraft. So this is only to tell you that nonlinearities are not things to fear, but things to learn how to deal with. Now, the simplest way you can deal with nonlinearities is by saying, well, so my nonlinearity is appearing as such. Okay. What I'm going to do is I'm going to linearize it around the operating point that I'm interested in. In this case, 0. In that case, some positive point. In this case, some negative point. And in the vicinity of this nonlinearity, we can indeed approximate its behavior by the corresponding tangent line. This is a completely standard procedure that really makes life much easier. Mathematically, we can write that if this is the input I, and that is the output O, such that we get that the output is a function of the input, then the linearization process about an input of a specific value is going to follow the Taylor expansion. O is equal to f of I0 plus delta I is equal to f of I0 plus partial f partial I expressed at I0 times delta I. So this linearization procedure works in many different contexts. If the function of interest is not a function of a single variable, but the function of many variables. Then we can do a more abstract yet totally real linearization process. For example, suppose that the sine of x times y appears in your equation. This is unlikely, but imagine that sine of x times y appears in your equation. And then you are interested in linearizing it in the vicinity of x0 equals 1, y0 equals 2. Okay, where we use radians. Then we can write that sine of x times y will be equal to sine of x0 times y0 plus delta. Oh, hold on a second. So a function of the linearization process for a function of several variables works exactly the same way. You have, for example, a function of x and y, and you would like to linearize it about some initial position or some operational position, x0, y0. Then we're going to write that f of x0 plus delta x, which is the difference between x and x0, y0 plus delta y, is also equal to f of x0, comma, y0 plus partial f, partial x, expressed at x0, y0 times delta x plus partial f, partial y, expressed at x0, y0 times delta y. Let's look at an example when f of x, y is equal to sine of x, y. This is unlikely in practice, but we can try. We try x0 is equal to pi over 3, and we assume that y0 is about equal to 1. Then sinus of x times y would be equal to the sine of x0 plus delta x times y0 plus delta y. And we can rewrite this as, using this formula, as sine of x0, y0 plus partial f partial x expressed at x0 will be plus So we use the chain form. We use that partial f partial x is going to be cosine of x0 comma y0. That's the first time. Okay, and then we have to use the chain rule, saying this is partial f partial x times the derivative of x times y, which will simply be y. And so the value at 0 will be cosine of x0 times y0 times y0 times delta x, plus, likewise for y, cosine of x0 y0 x0 times delta y. Now x0 and y0 are pi over 3 and 1. Therefore, this is equal to the sine of pi over 3, which is square root 3 over 2, plus the cosine of pi over 3, which is 1/2, times y0, which is 1, so I can just erase that, times delta x, plus, likewise, 1/2 times x0, which is pi over 3, times delta y. And so, square root 3 over 2 plus 1/2 of delta x plus 1/2 of pi over 3 times delta y is the linearized expression for f in the vicinity of pi over 3 and 1. We now can talk briefly about nonlinearities as they appear in equations of motion. The simplest example would be that of a pendulum. A pendulum is typically attached to an attachment point and contains a tip of mass m and a rod of length L and typically mass 0. This type of pendulum, if you assume it's not damped, is subject to gravity and the restoring torque of gravity, together with, of course, the reaction force here. When we take the equation of moments about this point, which we write h dot is equal to the sum of the moments, which is in this case minus mg times sine theta. By the way, theta is measured like this. This is the angle that the rod makes with the vertical. Then we actually have the equations of motion, given that h dot is equal to I times theta double dot, where I is the inertia of this guy, which is simply ml squared, therefore ml squared times theta double dot. And we obtain the equation ml squared times theta double dot is equal to minus mg times sine theta. We can simplify the equation. I forgot an L here, okay, that is the expression of the moment. I need therefore to add it here, and then we can remove this L and just say that the other way of expressing this equation of motion is like theta double dot plus G over L times sine theta is equal to 0 with some initial conditions. Now, the sinusoidal element is, of course, not a linear element, but we can linearize it. For example, about theta is equal to 0 by writing sine theta is about equal to theta. That leads us to the linear equation of motion, theta double dot plus G over L times theta is equal to 0. Assuming the initial condition theta dot is equal to 1 radian per second, then we can use this expression to obtain a solution to this problem using the Laplace transform. We simply write that this is equal to s squared times theta in the Laplace domain minus s times theta dot of 0 and plus G over L times theta is equal to 0. In other terms, theta times s squared plus G over s is equal to s, because theta dot is equal to 1 radian per second, and therefore theta is equal to s over s squared plus G over s, which, if my memory is correct, means that the solution will be theta of t is equal to sine of t, and that is the end of our derivation. That assumes that G over L is equal to 1.